Hello and welcome to our last lesson, video lesson 24, where we're going to work some examples on buckling. So for our first example, we want to figure out the maximum load that the column can withstand. We know that the allowable stress that the column can take is 15 megapascals, and Young's modulus E for the column is 12 gigapascals. And the column's cross section is 10 centimeters by 10 centimeters. So this is very much like a 2 meter tall fence post or a deck post. So about 4 inches by 4 inches, 2 meters tall, or about 6 feet. So those are fairly typical values for wood. So you can think about it sort of like a wooden fence post that's just undergoing a compressive loading, and we need to figure out how much load the column can resist. So we're modeling the column as having pinned ends, and we have a doubly symmetric cross section. So buckling might happen in the plane like this. Buckling might happen out of the plane like this. Either way is a possibility, but it should be the same because the section is doubly symmetric. So we're going to use this is the standard case for the Euler buckling load. We don't have to worry about alternate end conditions. We are pinned, which is what Euler derived the original buckling formula for. So here the critical buckling load is equal to pi squared EI over L squared. All right, so what's I? That's BH cubed, or in this case, since B and H are the same, S to the fourth over 12. That's 0.1 meter to the fourth over 12, or that is 8.3 times 10 to the negative sixth meters to the fourth. We now have everything that we need to figure out the buckling load for the column. So the critical buckling load for the column is pi squared times our value of E, which is 12 gigapascals, or 12 times 10 to the ninth newtons per meter squared, and then multiplied by 8.3 times 10 to the negative 6 meters to the fourth, divided all by 2 meters quantity squared, and then we would get a critical buckling load of 246.74 kilonewtons. Well, we need to check whether we've exceeded the allowable stress for our column, and our allowable stress times our area would give us another alternate loading for the column that would be the maximum load that the column could take, and we would need to take the lesser of this load or the critical buckling load. So the allowable stress in the column times the column cross-sectional area is 15 times 10 to the sixth newtons per meter squared, or 15 megapascals. And the cross-sectional area is 0.01 meters squared. And that gives us a critical loading based on the allowable stress of the material of 150 kilonewtons. So hence we would take the lesser of those two. So the maximum load that the column could withstand would be P max equal to 150 kilonewtons. Now let's take a look at a similar problem, except we now no longer have a pinned end up top and our base is fixed. Same column cross section, same height, same values of the material properties, same sigma allowable, same E. Now remember, for the case where we have the fixed free condition, we have to think about the column deforming this way, and it's sort of like we have the pinned case like this. So it's like the column would be equivalent to a pinned column that is twice as long, so the effective length factor K is equal to 2 for the fixed free case. So KL is equal to 4 meters. I is the same as it always has been, and that would be 8.3 times 10 to the negative sixth meters to the fourth. So if we're interested in the critical buckling load for our column, I would have pi squared EI over the quantity KL squared, which would be pi squared times 12 times 10 to the ninth newtons per meter squared times 8.3 times 10 to the negative sixth meters to the fourth, divided by the quantity 4 meters squared. And that gives me now a buckling load of 61.685 kilonewtons. So you can see that by doubling the effective length, we dropped the strength by a factor of 4. So there's an inverse square law. So we would compare that with sigma allowable times the cross-sectional area. That's the same as it was last time of 150 kilonewtons. So now the maximum load that this column can withstand is 61.685 kilonewtons. We're going to do one more example. I want to talk now about weak and strong axis buckling. So I've got a column here. It's got a rectangular cross section, and the longer side is coming out of the page on the cross section. The shorter side of the column is in the page. So the longer side is coming out, the shorter section is actually in the page. And the weak axis is braced at mid-height. So we would just put in a brace to keep the yardstick from buckling out. So it's a really big yardstick, but you get the idea. It's a rectangular cross section. So we put the brace on the weak axis at the mid-height point. When we do that, we're going to force a buckling shape that looks like this blue line that's sinusoidal. So what have we really done by bracing the column at mid-height in the weak axis direction? Well, what we've done now is we've shortened the column to half its original length. So a column that would have been 2 meters long is now effectively 1 meter long in the weak direction by including a brace. But we haven't included that brace in the strong axis direction. So we are going to take a look at the strong axis buckling out of the page. And if it buckles out of the page, it's going to come out of the page along this red curve because we don't have any bracing along the length in the strong axis direction. So we need to take a look at buckling for both axis directions. So let's start with the weak axis direction. I is going to be equal to BH cubed over 12. In the weak axis direction, B is equal to 10 centimeters and H is equal to 5 centimeters. So we would have 10 times 5 cubed over 12 times 10 to the 8th equals 104 times 10 to the negative 8th meters to the 4th. But for the strong axis buckling, what we have is I equals 5 times 10 cubed over 12 times 10 to the negative 8th meters to the 4th, or 416 times 10 to the negative 8 meters to the 4th. So for the weak axis, I have an effective length of 1 meter. For the strong axis, I have an effective length of 2 meters. So I would apply the Euler buckling formula for both cases. I'm going to use the formula P critical equals pi squared EI over L squared. Pi squared times 12 times 10 to the 9th newtons per meter squared times I of 104 times 10 to the negative 8th meters squared. Well, I didn't tell you this up front, but I will tell you this now. E is equal to 12 gigapascals for the column. So when I apply the Euler buckling formula, it's pi times 12 times 10 to the 9th newtons per meter squared times 104 times 10 to the negative 8th meters to the 4th divided by 1 meter squared. That gives me an effective, that gives me a Euler buckling load of 39.2 kilonewtons. Doing the same thing for the strong axis direction, I would see that my moment of inertia went up by a factor of 4, but the effective length doubled. So this denominator increases by a factor of 4, but the numerator increases by a factor of 4 as well. So the column would have an equal strength of 39.2 kilonewtons in both the strong and weak directions. So which direction buckles first? Well, it would depend on if we had a little bit of eccentricity one way or the other to the applied loading. If it was applied a little bit off of center and it created a little bit more bending in one direction than the other, we would be able to know which way the column would buckle. But it would buckle at about 39.2 kilonewtons either way. So that gives us the strength of the column when we consider both the strong and the weak directions. And it's possible if I had braced this at third points, if I had put a brace here and here for the weak direction, and I had the strong axis direction, it's possible I could have induced strong axis buckling with those particular braces. So that is the end of video lesson 24.